let's actually dive into our notes for 6.4. First off, here are the first 3 rules that we just mentioned in the last video. That if we are multiplying, we multiply the r's together and add the thetas. If we are dividing, we divide the r's together and subtract the thetas. And if we are raising it to an exponent, the power rule, also called de Moivre's theorem, as we mentioned in the last video, we raise r to that exponent and multiply the theta by that exponent. So we're going to show you how all of this works with these 2 examples here. Now, before we get started with these examples, we need to change them into polar form. So we're going to start with that. I want you to take these 2 complex numbers. You're going to find the radius, aka the modulus, and I want you to find the theta, aka the argument of these 2 numbers, so that you could then write it as r cis the argument. And I want you to do that for both of these complex numbers. So pause the video, find your modulus and your argument so that you could write them both in polar form, and then come back to check your work and see how you did. Let's check your work. For z, you should have gotten 4 cis pi 6. Radius is 4, or aka modulus is 4. The theta is a unit circle theta, 1 over root 3. Graph where the point is, 2 root 3 comma 2 gives us that point right there. And that is obviously a pi 6 angle, so the argument is pi 6. And for w, we got our modulus or radius to be 2. And I graph the point, -1 comma root 3 puts me right there. Once again, that is a unit circle value. That is at 2 pi thirds. So w is 2 cis 2 pi thirds. Now that we have them in polar form, let's look at doing some of these operations. First, let's do z times w. Now, like we talked about in the first video in this lesson, I could absolutely just take z and just take w and FOIL or distribute them together to get my answer. That is a totally valid way of doing this. That works algebraically. However, we just learned that for the product rule, instead, let's multiply the modulus and add the thetas, add the arguments. So let's take the 2 modulus, that's 4 and 2. We're going to multiply those together, and then we're going to add the thetas, or the arguments. So this gives me 8 cis 5 pi 6. And now, let's just simplify that. So that's going to become 8 cosine 5 pi 6 plus 8 sine of 5 pi 6. Let's take that up there because cosine of 5 pi 6 is a unit circle. That's -√3 over 2. Plus 8 sine of 5 pi 6 is also unit circle. That's 1/2. So this is going to become -4√3 plus 4i. And look at that. Exact same answer we got if we just FOILed or distributed these together. Same exact answer, except we did it from polar form. So when it's in polar form, we multiply the r's, we add the thetas, and then we simplify it all out to get the same thing. Like I said, both methods probably about the same amount of work. You've got your FOILing algebraically here, or changing it into polar form during your rule and then changing it back to rectangular form here. However, the more complicated the numbers get, the easier the polar form becomes than trying to do it like this. For example, let's look at the next one. Here, I want to do w to the 5th. That would be -1 plus I root 3 to the 5th. Distributing or foiling that thing 5 times would take forever. That, algebraically, is not fast, nor is it easy. However, with de Moivre's theorem, let's take the modulus, raise it to that exponent, and the argument, or the theta, and multiply it by that exponent. So I'm going to take my modulus, which for w was 2, raise that to the exponent, and then take my argument, which was 2 pi thirds, multiply it by that exponent, and that gives me 32 cis 10 pi thirds, which I can then simplify. 32 cosine of 10 pi thirds plus I 32 sine of 10 pi thirds. And 10 pi thirds is on the unit circle. I have 1 pi third, 2 pi third, 3 pi thirds, 4 pi thirds, 5 pi thirds, 6 pi thirds, and then keep going. 7, 8, 9. There's our 10 pi thirds right there. So if I take those points from the unit circle, cosine of 10 pi thirds is -1/2. Sine of 10 pi thirds is -√3/2, which gives me -16 minus 16I root 3. And there's our answer, which is way faster than algebraically multiplying that out 5 times. If I tried to do that algebraically, it would have taken me forever. In this case, the more complicated the problem gets, the faster the polar form becomes. This is way faster than multiplying that out 5 times. Last one. Let's try the division. Now, I actually would like you to try this one on your own. Use your division rules. We already listed them up here. For dividing, we divide the modulus and we subtract the arguments and then write them out like this and simplify it to find your answer. So pause the video, do z divided by w, and then come back to check and see how you did. Let's check your work. So I had divided the modulus and subtracted the thetas to get 2 cis of -pi/2. Wrote that all out. Just a reminder, -pi/2 on the unit circle is down there, clockwise pi/2. So then cosine of -pi/2 is 0, sine of -pi/2 is -1. Simplify all that to get -2i. And I also wrote over here the algebraic way. So if I'm dividing these two, I multiply by the conjugate of the denominator, FOIL everything out, simplify, simplify to get -2i. So in this case, I would argue the polar form is actually way faster than doing this algebraic way, which, as I said, the more complicated the problem and the numbers get, the faster this polar form will be than trying to do it algebraically. That's why we have these polar form rules. It lets us do all of these things a lot faster the harder the numbers and the problems get. Now, there's one more rule we haven't talked about, as we mentioned in the first video, and that is how to do roots. That is what we'll spend the rest of the lesson on, is how to take square roots, cube roots, fourth roots of these complex numbers. That's what we'll start in the next video.